you know. Now, the test isn't until after the break, but still, you need to revise these things. We have our mechanics test on Friday. Yep. Okay, stationary waves. Yep. Continue. You got this? So, what is a stationary wave, also called a standing wave? Well, it's a wave that oscillates in one constant position. It can arise in a stationary medium as a result of interference between two waves traveling in opposite directions. So, the picture really helps here. Before you write this down, let me just explain with the picture here. So, if you see, what you have here is a string. But the string is vibrating, and it makes a wave like this. And this wave isn't moving anywhere. What's happening is this wave, when it tries to move, it hits here and travels backwards. So you can't really see what's happening, but in slow motion, what's happening is this. We have our wave like this, and it's fixed here and it's fixed here. And then it moves down here and it moves up here. So then it goes like this. And it does this so quickly that it looks like this, because it moves so fast. So this wave does not move away. It's trapped here and here.
And the center doesn't move.
And this point doesn't move as well, yeah. So this is a standing wave. Another way you can make a standing wave is if you have a rope and you put the rope here and you hold it and then you start to shake it, it will make a wave, and if you get it right, the wave will not move forwards and backwards. It will just start to move up and down. Now, how can you do that? So let's imagine here you're standing with the rope and it's tied to the wall here. So if you give it a little flick, what's this one called? Transverse wave. So if you make a little wave like this, what will happen is it will move through the rope, hit the wall, and then come back to you. So you go flick, and it goes up and back. Yeah. But if you can make the wavelength the same as the distance here, so if you can make a bigger flick, what would happen is it will try to move to the right, yeah? It will try to move to the right like it did here, but it can't because it's already finished. So it immediately bounces back. But it can't move back because it's already finished. So it cannot move forwards or backwards, so instead just flips upside down. And so this is the picture explanation, and here it is in words. So I think it's easier to understand this as a picture, but this is the formal definition. So now you can write it down. You have this? Yeah? Continue. Yeah, okay, so some more terms. Node and antinode. Node is the point on the standing wave that has no amplitude, and an antinode is the point on the wave that has maximum amplitude. So in my picture here, or if I go back here for a moment, just one sec. You see this point here and this point here? They don't actually move. Whereas this point here moves up and down a lot. Can you see that? Yeah. And here this one moves up and down a lot, and this one here up and down a lot. So these points have names. They're called nodes and antinodes. So the antinodes are the points at the top of the peaks that are moving up and down a lot. Whereas the antinodes are the ones in between, and these don't actually appear to move. Yeah, I'll write this down, yeah.
Oh.
It's good for your English. You told me English was your favourite subject.
No.
Sure. You said it was subject number 4, the best one. Highest score. 1, 2, 3, 4. I thought that physics was your worst. It was number 1 at the bottom. No? No? Okay. Yeah. You got this? How's the essay going? Is it going?
Slowly.
I was hoping to get drafts on Monday.
Oh yeah, since you didn't today.
Okay.
I wrote something for this.
Doing apprentice or send?
Printed.
With
With the cover sheet to class on Monday.
Class. So
The
it's
class.
Not before 9, right?
No, because it was supposed to be due last week with Sylvia, so I'm taking it in class next time. Okay, you got this?
Yes.
Okay. Go on? Yeah, okay. If you know the distance between the nodes or the antinodes, then it's very simple to know the wavelength. So if we all look at this together, we can try and work it out. So here's the wave moving up and down. So it will look like this. This is a node, this is a node, and this is a node. And let's imagine we know the distance between the nodes. Let's just call it x, for example. What would be the wavelength? No, 2x. Yeah.
Half.
Here to here is x.
Okay.
That's only half the wave.
But
So 2x. So if you know the distance between the nodes, double it to get the wavelength.
so
But
it
it's
will
same.
be 4.
One sec. Huh?
But it's same.
What's the same?
distance is same.
Oh yeah, between the nodes it's the same, and between the antinodes it's the
so-
same. So double any of these distances.
We have one.
Yeah, if I tell you the distance between the nodes, double that. If I tell you the distance between the antinodes, double that.
But it's same.
I know it's the same.
So it's just one. Right.
Yeah. Use either. It depends what I tell you.
No, she said that the wave is the same. Like this is not a half wave. This is a full wave. Why should we multiply by 2? That's what she said.
Because
Is it? I don't understand this question.
From a node to another is not a full wave. It's a half wave.
it's a half a wave. That's why we.
Yeah.
That's why we multiply by 2.
here to here, or here to here, node to node, that's only half of the wave. Yeah or no? Tell me, what's confusing here?
Well, this is a wave.
Mm-hmm.
This is not. This is the distance.
Yeah.
We multiply it by 2 because this is one wave. This is only half wave. This is not, but it's only half a wave. This is one complete wave.
One wave has 4 nodes.
Let's see.
1, 2, or 3.
3 nodes, yeah.
Yeah.
For example, if you knew the distance between the antinode and the node, let's call this x.
By 4.
Yeah,
Yeah.
the wavelength would be 4x, because this is only a quarter of the wave.
Now it has off.
Yeah,
This is not
is it though? I don't understand what is hard.
It's not.
Forget about the nodes and the
I don't
antinodes
understand.
and
This
just make
is-
the wave. That's it.
But it's just the distance, like this, it's just from this to
Yeah.
this. So why have
But
to?
this from this to this is half.
This is a half. This is a half wave.
This is half a wave.
This is a full wave.
Yes. Exactly.
Here's my standing wave. This here is the wavelength.
But
This is called a
No.
node, and this
No.
is node, and this is moving up and down, and this is moving up and down. I'm saying if you know this distance, you know it will be half the wavelength. Yeah? Or what about this distance from here to here? That's a quarter of the wavelength. Here to here is half a wavelength. This one to this one is a quarter of a wave. Because look,
Do you understand?
this is only a quarter of the wave. This one here is half the wave. This here is a full wave. Oh no, she doesn't believe me.
She's calculating something.
She's thinking about something.
Yeah. This is one wave. This is one wave. Can you see? And this is not, and this is not.
This is half.
Half a wave. This is one wave, this is half a wave. We have this distance, we multiply it by 2 to get the full wave.
What
That's it.
about one of four?
Yeah, why 1/4? Go explain it to her
Yeah,
then.
this is 1/4. We multiply it by 4 to get 1, 2, 3, 4, which equals the wavelength of the full wave.
1,
Because
2, 3, 4. This is one full wave.
All
This
of
is
them.
only a quarter.
Why lambda over 2 and lambda over 4?
Because this,
Because this is half of it.
the distance from a node
A node
to
to a
another
node.
is a half. And the distance
Oh,
from a
so
node to
lambda
another.
you know,
over
is a
2
quarter.
is...
Half of it. Lambda over 4 is a quarter from a node to an antinode. This node, antinode, node, antinode, node. You think about it tonight. You sleep on it. You think about it.
I accept that.
You accept it. Okay. All right. It's just, yeah, it's one of those things where you have to see it, I guess. Okay. So let me draw this, which I did. Right, so continuing with standing wave. If a string is held at both ends, the ends become the nodes. Yeah, okay, so the length of the string then becomes a measure of which waves the string will entertain. The longest wavelength is called the fundamental. So this maybe, since Iyad, you play the guitar, don't you? Yes. So you can imagine here and here is fixed, and here we have a string. So you can pull this string up, and you can make this shape. You can pull it up, and then you let go, and it goes up and down. And you can see this on the guitar string when you pull it up. It goes up and down, okay? let's call this distance x from here to here. What would be the wavelength of this wave? No?
X, two.
2x. Very good. Because
it goes up and down.
yes, what you can't see here is this is actually only half of the wave. What you can't see is the other half.
Yeah.
So you're right, 2x. Yeah. But of course you could have done it this way. You could have made the wave like this. And in this case, what would the wavelength be? Again, if this is x, it will be x. Yeah. Now, you could have done it this way as well. Up, down, up, down. Now it's getting a bit harder now to see. This is x. So what would be the wavelength here?
Half.
That's a wave and a half.
Very good. It's a wave and a half. So this is one wave and a half. So you could say, for example, 1.5 wavelengths is equal to x.
Yeah.
So 3/2 wavelength is equal to x. So the wavelength will be 2/3x. Yeah, it's getting a bit harder. But anyways, this is the biggest wave you can make, right? These ones are, the wavelengths are getting smaller. So the biggest wave is called the fundamental wave, or sometimes called the first harmonic. But unfortunately, I think sometimes people call it the zero harmonic. But for this course, when I looked at the exam, he sticks to first harmonic. So I'm just telling you this in case you see it in a book. So you can call this the fundamental wave or the first harmonic.
The half of it?
The biggest wave you can make. Who's this going to be? Oh, it's Dennis. What's up, Dennis?
Hi, Derby. Do you have a board pen spare? No.
Do you know what, Dennis? I have nothing except my laptop and projector.
Yes, me too. I came very empty.
Oh, you came with your laptop and projector as well?
I even have less than you.
Okay, all right. All right. Did you write that down? The name? Yeah, sorry, I have it actually here a bit neater. Yeah, harmonics. So you have the fundamental, or it's also called first harmonic. Do I have pictures? Oh, look here. Here's nice pictures. So this is called the fundamental, or the first harmonic. And then the next one, of course, the second harmonic, and then the third harmonic, and the fourth harmonic. So I drew... Wait, I'm talking. No, but I'm talking. Wait. I drew the first, the second, and the third harmonic. Please note, the first harmonic is also called the fundamental harmonic, or the fundamental wave. Okay, now Mahmoud, what are you asking me?
About it's going faster, yes?
No, actually the speed is the same. At least I think it is. I don't think the speeds change here. It's still going up and down with the same speed.
The wire of the guitar.
I don't think it's any faster. I think it's the same speed. It's just the shape that's different.
Why then? Yeah, why?
Why is there a difference?
Why is there a difference?
You can make the difference depending on how you strike it. If you're just using your finger, I think you can only really make the first harmonic, because you just pull the string up and let go. You flick it. Trying to make the second harmonic with your hand is too difficult. You need to use something else, like, do you know a tuning fork?
Yeah.
Yeah, you can do this. If you hit the guitar string with the right tuning fork, you can make the second and third harmonic. But with your hand, you can't. What happened?
The notes.
I don't understand your question. Do you remember the example with the boy with the string against the wall?
Yeah.
Yeah? It's just a matter of changing the,
Okay.
like the effort.
I got.
Yeah? Okay. Did you draw this with the names? Okay, you should. Okay, continue. Yep. Okay. So you don't really see this in guitar strings, but you would see this in piano strings more. Do you know piano?
Yeah.
So if you play? Nice. So if you look at piano strings, they can make the different harmonics like this. Now, you can get sound waves as well in a pipe in the same way you can get the waves like this. So when a sound wave is formed in a pipe, there'll always be a note at the closed end and an anti-note at the open end. Now that's really, really important. So if somebody is playing a pipe, what's happening is, what's making the sound is a sound wave inside of it. The end which is open, there's always an anti-node here, and the end that's closed will always be a node. So for example, you might have something like this, and this is vibrating up and down, and this one here is a node. That would be the first harmonic, but you could have drawn it like this. 1 second. Yeah. And this would be the second harmonic, and so on. And each one has a different sound to it. This is what makes the different sounds. So if the pipe was open at both ends, then there must be antinodes at both ends. So the first harmonic would look like this. There has to be an antinode at both ends. Yeah? And the second one, oh my goodness. No, that's yeah, okay. That would be the second one. So how many waves have I got here? 1.5. Yeah, yeah. So if I know the pipe length is x, then I could say the wavelength would be 2/3 x. Then.
Why 2/3?
This is 1.5 wavelengths.
It's not a half.
Not a half, no.
It's half, it would be 3/2.
If it was half, then it'd be 2 then. It's upside down. So, the most important thing that you need to take from this with the sound waves in the pipe is that when it's closed, it's a node, and here when it's open, it's an antinode.
What about
When you whistle, that's not really the same thing, because you need something where you can make a standing wave.
Like a toy, because I cannot whistle.
Wait,
It's okay.
Because it's hard.
you said, so a whistle is not a standing wave? Is that what you're saying?
Yeah, whistle's not a standing wave. A standing wave, a sound wave that's a standing wave. Well, you know what? No, maybe it is actually, but it will be inside your mouth. Do you know what I mean? Yeah, because you kind of make like a small pipe.
That's an antinode.
Right.
Okay.
And explain it.
Okay.
When you whistle, you make a small pipe. Yeah. Now, would it'd be open here and at the back closed, because there's no air coming in here. Yes. So I don't know. What would we say? Hang on. Here's our mouth.
What is this?
It's a mouth.
Lip?
Yeah, really.
What is the two balls?
That's the lips.
Okay.
It's not beautiful, I know. So this distance here would be x. So I think this would be a standing wave. This one here would be a node, and this one here would be an antinode. So the first harmonic would look like this. Yeah, so the wavelength would be what? 2x, wouldn't it? No, it's a 4x, isn't it? This is a quarter of it. Yeah, it's only a quarter. It needs to continue down like here.
Yeah.
That's 4x. Now, when you change the sound, like I can't quite do it, but the different sounds. There you go.
Okay.
The different sounds represent different harmonics. Okay, so what you're doing is you're making a standing wave and you're changing which harmonic, which means you're changing the wavelength. For example, if I do the next one, like this, the wavelength, does it get bigger or smaller? It gets smaller, yeah, and this makes a different sound. Okay, so please make careful note of that. Closed is a node and an open end is an antinode. You won't be told this in the exam, and you're sometimes asked it when you have to draw. So.
I'm asking about something.
Yes.
When you eat a gum and you make a like you're making
The bubble, yes.
Yeah. Does it affect or no?
Yeah, affect what?
I mean is there a node inside?
No, there's no sound.
No. If there's a sound, there will be
I don't think you can whistle and blow a bubble at the same time.
No.
That would be impressive.
No, I'm asking about when you are eating gum and you wanna make a bubble.
Yes.
Yeah, it will be does it will affect on you when you want to whistle?
Yes. That you can't whistle.
Mahmoud, you can't blow a bubble on this.
Yes. So the effect, yes, it does. You say it's Tom and Jerry? Yeah, it does. All right. Okay, continue. So this is how musical notes are made. This is how you make musical notes. Okay. What's wrong? Oh, he's got an explanation, is it? Nice. Good. You hold on to that. Can you note this word, please? This word resonates is a verb. To resonate, it means, if I go back to my beautiful picture here, when there is a standing wave, standing wave of course is a noun, we say that it resonates. Resonates is the verb. So please note the verb here, resonate.
So, yeah, you mean...
Means vibrate.
In a question,
Yeah, you could say a standing wave causes it to resonate. Or you could make resonate into a noun, resonance, and there's synonyms for resonate, which is vibrate. So it's just vocabulary. Okay. Let's do an example now. Yeah. Okay. So I've got 2 questions to do. Okay. So can you write or draw this, please? I think in fact you could even do this one. See how you get on. Try this one. You're sick? Try this one. You can draw? Draw a picture. You know vibrate? Vibrate.
So the first X is
Like
2.
shake. Move.
X is 2. Yeah?
Let's see. What did you draw? Can I see your drawing?
I'm asking X is 2.
X is 2. Which one? Point to it. Yes. Did you get it? Draw it? No. Because you can make a bigger wave than that. That's not the first one.
Ooh.
Yes. So what is the wavelength? I think so, yeah. So like if the wall is here and the boy is here, the first harmonic he can make here, yeah, is 2 meters. So the wavelength will be 2 times 4 meters. Now it's not really 2 meters because I said the rope, its length is 2 meters, which means this here, is that actually more or less than 2 meters? Think carefully. Less than 2 meters. So it's not quite 4 meters, but we'll say it's roughly 4 meters anyway.
Okay, why is it less than?
Because the rope length is 2 meters, not the distance. So yeah, because the rope is bent. This distance is 2 meters, which means this can't be 2 meters, because this has to be longer than this. So maybe this is like 1.8 or something. Anyways, that's not really what I was testing here. Right. Okay, so try this one. I think again you might be able to do it. Oh yeah, actually, you know what? You might be wondering how can you make sounds with certain frequencies. This here is called a tuning fork. Have you seen them before? You've seen them before. Fuang, have you seen this before? No, and printed on this would be a number like 500 hertz. And what would happen is you take this fork and you hit it on the table and it starts to shake and it makes a sound. And the sound wave here will be exactly 500 hertz frequency.
However, you hit it harder.
Yeah, it doesn't matter if you hit it hard or not, it'll make 500 frequency.
How can we change it by changing the...
You can't, it's built to make 500.
No, I mean like, that's another one. What's the difference?
Oh, I think they'll change like the distance here or here. I don't actually know. They come in a box, you know. Different. I think the smaller ones have higher frequency. Yeah. So it's the size. So maybe this one would be 300 or something. And they come in a box. And you use them with pianos to tune them, and maybe guitars too. You have a box of these?
No.
Okay. Nicer.
The wave.
Oh no, I'm just saying. In the question, I said there's a wave of 500. And I said, how would you make a sound wave of 500? And you can use things called a tuning fork. You know fork? Like what you eat your food with. Yeah. Knife and fork. Yeah. So a tuning fork.
Chopstick.
Oh, of course, chopsticks. Sorry, so silly of me. Yeah. Anyways, I just thought maybe you've seen these before. Has anyone? I know you've seen them. Have you seen these before? No. Adnan?
No.
Okay. Right. Okay. Anyways, this is a stationary sound wave is formed in a pipe. So what happened here? I'll draw it for you. You had a pipe. It was closed at one end and open at the other end. And then somebody had a tuning fork, for example, and this was set to 500 hertz, and they hit this fork off the pipe, and it made a wave inside the pipe here from this. So the question is now, what is the speed of sound? Now you actually have enough information here, because if you think about it, I know this distance, I said it's 17 centimeters. So can you know the wavelength if you know this distance? Yes. And if you know the frequency, can you know the speed of the wave? Yeah, V equals lambda F. So you have everything you need to know to work out the speed of the sound wave, i.e. the speed of sound. So calculate and see what you get. Now, before you start, you need to draw the first harmonic.
First fundamental and first harmonic.
No, I think the fundamental is the same as the first harmonic, but then I think some books might go first. after fundamental. But for this course, fundamental and first is the same. So the wave inside of it, this is the wave inside of it. So what's the wavelength? What's the wavelength? No, 4. This is only a quarter of the wave.
But it's
How can I know it's a quarter or
In the
You can see from the picture. You can see in the picture.
Yeah.
It goes from the middle up to the top, but it still has to go.
From the top to the middle.
Oh wait, no, is it a quarter or is it a half? Hang on. Let's look carefully.
It's a quarter.
No, hang on. Let me draw a line here to help.
It's a half, I think. Yeah, it is.
Yeah, because it still has to go.
One more.
Did I draw that? It's hard on the side. Yeah, it's like a sine. You remember in math, sine? Sine starts in the middle, goes up, back down to the middle, and then back to the end like this. This is one wave. So here to here is only half. It still has to go down and back up. So in this case, it will be 4 times 0.17. There's no rule here, Musharif. It's a picture that helps you. You need to be good at drawing pictures. I know.
I'm not happy.
I could feel your thoughts. 0.68. So V equals lambda F, which equals, did you say 340? Yeah. Yeah, no, 340 is the answer.
Oh, okay, the V. No, the I thought you said
Yeah.
the V. I just calculated the V.
Is that good?
Yeah.
Okay.
Oh,
Okay.
no.
We use this formula, V equals lambda F. Do you remember this one?
Yeah, I know.
Yeah.
But
We know the F,
the 4x thing.
and we know the lambda.
but to determine it is
This,
2x.
yeah,
You don't like this.
2 is yeah.
you and Fuang, the two of you really don't like this. All I can say is, you can watch the video again and think about it. You know, do you take the bus home?
Yeah.
Yeah, as you're on the bus, you can think about it more. You can dream about it.
Or you can read my very deep.
So
Yes, or you can read Adnan's notes he made.
no, we can say in a pipe it's always 4x is the first one. Can we?
Yeah, you can. But see, I don't like remembering things this way because you'll muddle them up. Also, if this was closed, then it's not going to be 4x because it has to go from node to node. So it's not 4x now, it will be 2x.
Half.
Yes, you see. So it's a little bit hard, but with practice it becomes easy. Yeah. Okay. Yes.
No.
Interesting, huh? Now, you'll get plenty of opportunity to practice now with your pictures. And we've got, oh, perfect, right. So my idea is you can work on this for 10 minutes, then I'll do the answers.
Okay.
Yeah? Harp is, if I have an Irish coin, I can show you a harp.
Oh, this is it.
This is a harp, this instrument.
What?
This,
The set?
the picture. Here, look, keep that, that's a harp.
I want
Yeah, I say it.
Do you know this? For making
Yeah.
music.
Yeah, I know that.
You know this instrument?
yeah.
Yeah? So
I
you
know
pull the
that,
string.
and I can have it.
You can have it, there you go.
Yeah, I say it. If I have a lot of time and I can buy something.
You might get a coffee if you have enough 5 cents.
Yeah, cool.
Yes.
I have
Perfect.
5 cents.
There you go.
To buy you coffee for weeks actually.
Yes. Okay, try this one now. So this is just like the string and you pull the string. That's all. That's all. It's just like the example with the boy against the wall. So if you have the string and you pull the string and let go, if this is 30 centimeters, what's the wavelength? 2, yeah, so it's 60. If you know the wavelength, and look, you know the speed here? 340. Can you know the frequency? Yes.
The speed is over the frequency.
Yeah. What? Open at both ends? Antinode and antinode.
Yeah, something like that. Antinode, the length is the antinode.
And the antinode.
Yeah, like that.
So, wait, that's half.
Antinode to an antinode is
Is it, or is it one?
Wait, it's first
No.
harmonic.
Oh, it's half, yeah,
It's half.
it's half. It makes an S shape.
Yeah.
It's only half a wave.
Yeah.
So it's 2.
2x.
2x.
Something like that. Yeah.
Which question?
Yeah.
2.
It's like that.
And S shape is half a wave? Is it?
Is it? Actually, that's a good question now. Or is it one full wave?
That's one full wave.
Hang on.
Or is it 1.5? I don't know.
I can't picture it, I need to draw it.
Okay, just wait.
Which one am I looking at? I don't need, it's okay, I'll just control. I got it!
What's a full wave like this? It's S shape.
I think it's one wave.
X. Okay, so it's X.
I'll have to draw it. Maybe as you're working on it, I can put the answers on the screen. So the first one, you've all finished the first one, yeah?
Yes.
What did you get for it?
566.66.
Yeah, the wave.
Yep.
This is, look, this is the first harmonic, that's 30 centimeters, so the wavelength is 6, V equals lambda F, F equals V over lambda, which is 340 over,
0.6,
which is
566.67.
567 then,
Yeah, right.
hertz then. Okay, so number 2, I'll help you out, it's open at both ends. So what you have here is an antinode. Now, is this one full wave? Let me think. So if I start here, I have to go down. No, it's not. It's not a full wave. It's only half of it, yeah.
Yeah. 2 multiplied.
2 multiply, yeah. So the wavelength would be 0.8. Yeah, so the frequency again. What did you get for number 2, Iyad?
I still didn't.
425?
Yeah.
Then you pause and let us do 3 and 4.
Yep. It's getting harder though. Those were the easy ones.
Yeah, the exercise for me for 4 only. 5 and 6 are only.
That's for me, is it? Yeah, so in number 3, I give you the frequencies for the 3rd and 5th harmonic, and I don't tell you the wavelength or the length of the pipe.
It's quite easy.
Is it quite easy? Well, that's good to know. I thought it was quite hard.
Tie the 8th and then
I know that.
draw the
Oh.
5th and then
Yep. If you can draw the 5th and the 3rd. Show me beautiful pictures, please. What the heck is that?
the 5th.
That's the 5th, is it
Yeah.
really? Okay, alright, if you say so. Oh, come on, give it a try. You could at least draw the picture for 3 and 5 harmonics.
I have them.
That's the
That's the problem.
1 minute.
Before.
Yeah, I'll put it back now.
okay.
The frequency of
The 3rd harmonic, all of it is 3 weights or 3 sets?
One sec. I'll do it now in a minute.
the lambda of the 3 and 5 is equal.
No, different wavelengths because different harmonics. The 5th harmonic should have a smaller wavelength than the 3rd harmonic. The only thing that's the same for both is the speed, the V.
Which is 340.
340, yeah. Mm-hmm. 1, 2, 3, 4, 5. Alright, will we do it now? So this is closed at both ends.
Yeah.
So closed at both ends would mean a node and a node.
Yes.
So this is the first.
Okay.
The second,
2 I.
twice. Yeah, that's the second. Okay, so now it's third. Oh, this is the third. So anyways, here the wavelength would be 2x, wouldn't it? Here the wavelength would be x for this one. Yeah, this one here will be 2 over 3x, wouldn't it? Now, what about this one? This is the 4th harmonic.
Yeah.
2 ways.
2 ways. 1 more.
So then it would be x over 2. A half x then. Yeah, now can we try and make some pattern here so we don't have to do this if it was a bigger number. So this is 2 over 3x. This one here, maybe it's like 3 over 3x. I don't know what this one here, over 3, what would it be? No, that's not quite it. Alright, let's see what the next one is. 2 divided by 1, 2 divided by 2, 2 divided by 3, 2. Ah, this is what's happening. Look, yeah. This is 2x. This is 2x divided by 2. This is 2x divided by 3. This is 2x divided by 4. So the next one will be 2x divided by 5 then. Yeah, so what do I give you? I give you the 3rd and the 5th. So in the 3rd one, what's the frequency?
1100.
1100, and then the fifth one?
They ask for
Oh, what is the fifth one then? Here. So if you look at this picture, you know the F, you know the V, so you can know the lambda. Because you can say V equals lambda F. Lambda equals V over F. In this case, it's 340 divided by 1100. So that is 0.309. If I know the lambda, I can know the X, because what would the X be? 3 over 2 lambda. So I know that this X is 0.464 meters. And does that change each time? No. The length is the same.
Yeah.
So for this last one here, you can get the wavelength. The wavelength we said was 2 over 5x. That is 0.185 meters. So finally the frequency is V over lambda. So after all that we get 1833 hertz. I thought that was a bit hard. Some people didn't. What?
Quite easy.
You said it was easy.
05186.
Yeah. Maybe I wrote it down wrong. I'm tired. You get the idea. Okay, can we go on to 4? Okay, so this one now, I'll do this one with you. So a woman is working with a large machine that has 2 settings, fast and slow. When it's on slow, the RPM is 240,000. Does anyone know RPM? Rotation per minute. So it's like a frequency, but it's in per minute. But we don't want per minutes, we want per second. So I should divide this by, so it will be 4,000 hertz. This is when the machine is on, did I say fast or slow? Slow. So she's working on a machine, and when it's on slow, the frequency is 4,000 hertz. Okay, and then and strangely, when the machine sounds louder. So what I didn't make clear is the machine is loud when it's on fast. So I'll just draw it here. The machine has 2 settings, fast and slow. When she changes the machine from fast to slow, it actually sounds louder in her ear, which is surprising because you'd think if the machine is slower, it should sound quieter. And the reason it sounds louder is because in her ear, if I draw her ear here, the frequency is smaller, but now it's the right size for the ear. What happens here is a wave is formed inside her ear. And when a wave is formed, this will now start to vibrate. It will, remember the verb resonate, vibrate. So what's happened is the machine on the slow setting is the right frequency for the ear to fit in the first harmonic, the standing wave. So the question is, what is the size of her ear?
I saw videos about the bridge.
Oh, we're going to do a video now in a second. So let's calculate this, okay? What is the wavelength? The wavelength here. We have V equals lambda F. Do we know the V?
Yeah.
Yeah. Do we know the lambda? No. Do we know the F? Yeah, it was 4,000. So the wavelength will be V over F, which is 0.085. Now, how big is her ear? Is it 1 wavelength, a half a wavelength? What is it? A quarter of a wavelength? Which one is it? It's a quarter. This is a quarter of a wave, isn't it? So then her ear length would be this divided by 4, which would be 2.1 centimeters. So you know the ear canal, the part inside of your ear, you know, because it goes into your head, that's about 2 centimeters. Yeah. Now, who has a laptop? The speakers here don't work. Or who has a phone? You got your phone? Yeah. Go to YouTube. Yeah. And don't play the video, but Google sine wave 4000 hertz.
How many hertz?
4000. And Adnan, can you go to YouTube as well and Google sine wave, and we'll make his one louder. We'll say I don't know.
1,000.
No, bigger than 4000. So we'll say maybe.
I can't find 4,000. There's 400.
You know what? Type in 4 kilohertz, 4K hertz.
Okay.
Me?
Yeah. Now you can search for. I want yours to be a little bit bigger. So something like if they've got like 4,500 hertz or 4.5. No, don't play yet. Don't play.
Sorry.
But put the volume at maximum to get ready to play. Did you find it?
4.5.
Kilohertz.
Yeah.
Okay, play that on full volume.
Where is it? 12 hours.
It's just going to be a loop. Just play it. No, that's not it.
That's not a sine wave.
That's not a sine wave. Did you type in sine wave? You have sine wave 4. Okay.
Sine?
S-I-N-E.
Or sound?
Oh my God. Be patient, Stephen. Be patient.
S-I-N-D.
Yes. So what we're going to do is his phone. Look, his phone is like. That's it. Yeah, play that on full sound. Not yet. Wait. His phone is like the fast setting. His one here is 4.5 kilohertz. And then Iyad's one will be 4 kilohertz. And even though this frequency is smaller, I think it will sound worse in our ears. So play this one. Okay. No, it's okay. You won't die. Okay, stop.
It's in the phone.
It's not too bad. Now, play yours on full power. Which sounds worse? This sounds worse, doesn't it? No, stop. Stop. This one sounds worse.
Yes.
And the reason it sounds worse is because a first harmonic is formed in your ear. So your ear is resonating, it's vibrating.
No, can I do this?
Oh yeah, you need to print that. Yes?
Yeah.
Okay, so that was an interesting one. Okay, try number 5 now.
So it means if the F is the smaller, it will be
Louder? No, it's just this F is the right frequency to make a first harmonic in your ear. So he had 4,000. If he tried put on 3,000, it won't sound as bad.
Thank you.
See ya. Depends on the length of your ear. Your ear is smaller than my ear, so your frequency will be different to my frequency. Your frequency for first harmonic will probably be smaller than mine. Got 3,000? Let's hear it. That's not 3,000.
And
Oh, it's an ad. Oh. There's 3,000.
yeah.
Now I know it's annoying, but it's not quite as bad as 4,000. Maybe it's worse for you because it's smaller ears, lower frequency.
This is bad, yeah.
But not as bad as 4,000.
No,
But in the
Yeah.
the phone,
Yeah.
what?
What? The phone? The phone sometimes makes this sound, yeah? What'd you ask me?
It's
What's the frequency?
yeah.
Oh, I don't know. sometimes they send test signals down the phone. So for example, if Iyad has a phone company and I have a phone here, he might play 2000 frequency sound wave, and then I would listen, and maybe I have some machine to see if it is 2000. So it's a test sound. You see these on the TV as well. You know the one I'm talking about? Test sound. They check that the frequency is correct for what is transmitted. Let's have a look at 5 now. I think 5 will definitely have to see me do it, okay? So can we have a look at 5? A car is travelling 120 kilometers an hour between 2 radio towers. The signal increases and decreases as the car travels between the towers. The signal's peaks are 43 seconds apart. So what's happening here is you have a radio tower, and you have another radio tower here, and there's a wave coming between them, going between them like this. And in fact what's happening is a standing wave is being made between the towers. This is a radio wave. So when you're listening to the radio in your car and you're driving along, this is like the boy walking down the hall. It will sound, the signal will be strongest here and weakest here. And it'll be strong and weak, and strong and weak. Because what's happening is this is an antinode and this is a node. So it's strongest between the antinodes. So I tell you that they're 43 seconds apart. So to go from antinode to antinode takes 43 seconds. Oh yeah, we were joking last time about combining mechanics and waves. So here's one that combines them. And the speed of the car is 120 kilometers per hour. So what we'll do first is we'll work out the distance here using distance, speed and time triangle. So the distance would be the speed multiplied by the time. However, we want this in meters. So if we convert to meters, yeah, something like that. I remember it, isn't it? Yeah. 33, yeah. So the distance between the antinodes is 1,433 meters. So every 1.4 kilometers the radio signal is strongest. Now, if I know the distance between the antinodes, I can know the wavelength, can't I? So what would be the wavelength here? We have to double it, isn't it? Yeah, so the wavelength would be 2866 meters. If I know the wavelength, can I know the frequency? V equals lambda F. Lambda equals V over F. Now what's the V here?
V equals
No. What's the V? No. The V is C. Because it's not a sound wave, it's a radio wave on the radio. An electromagnetic wave.
But the radio wave is not alive. It's a constant.
No, but remember we said all those waves travel with C. All the electromagnetic waves travel with speed C. X-ray, infrared, yep, all C. Yep. Okay, so here we get the wavelength will equal then 104,675 meters. Is that what I was looking for? What was I looking for? No, what was the frequency? Oh, I went too far.
You just split the lambda by the frequency. You have to.
Oh, sorry. Thank you. Yes. F equals V over lambda. Yeah. So F is 104,676 hertz. Or if you divide by 1,000, 104.6 kilohertz. Now tell me this. Did you listen to the radio? So in Ireland we have radio stations. For example, there's a radio station called 103.8 or 104 or 106. These are the names of the radio stations.
Yeah.
These are the frequencies in kilohertz. So this radio station would be 104.6 FM, for example. News talk or something like this, yeah. I don't know what 104 is. I know 104 is music, and then 106 is news, maybe?
There is a channel for music.
Yeah, 103.8 and 104.
Every day we listen to music. Someone starts today.
Yeah.
And
Is it 104.6 for news talk?
I think so.
Something like this? Okay. Alright, so the last one now, it is the same as number 3. However, we get this in the exam, there's a small error. So what's happening here? Error. Mistake, yeah. So we said we have this, is it a standing wave is an open at one end pipe. So let's try our best. First, yes. Second. Third. No, this is not a full one. This is 1 1/4 quarter. Yeah, 1 1/4. So if this is X or L, then the wavelength would be, 1 1/4. 5/4.
1.5.
5 1/4 wavelength equal L.
How do you know it's 1.5?
No, 1 1/4.
1 part.
Oh, 1.5.
This is 1, and then we need
Yeah, but
quarter
the
more.
question is how?
This is the third harmonic, and we're told that the frequency is 1100
But
hertz.
is the third harmonic like this?
I sure hope so. Let's try again. This is the first, yes?
Yeah.
This is the second. Yes. And the second is 3/4. And then the third, one and a quarter. I know. Even I have trouble with this. Right, so this is the third. The fourth one, my goodness. I don't know.
1.5.
Let's try and figure out a formula, okay? So the first one we have, this is a quarter. Yeah. So the wavelength would equal 4x. Okay, we're happy with that.
Yeah.
Great. Okay, the next one?
2x.
No, because 2x would be if it was like this. But remember, it has to be an antinode here. So it has to go
4.
this one, which is 1 1/4.
4x multiplied
Huh?
quarter.
Isn't this a...
Oh, sorry, 3/4. 3/4.
Yeah.
So the next wavelength will be 4/3x. So don't worry, I can already see the pattern. The next one, 4/.
How is 4/3?
No, it's not 4.
4/5 is the next one.
Yeah, it's...
Okay,
so it's
4/1, 4/3, 4/5. So the fourth one would be 4/7x.
Okay.
And then the fifth one would be 4/9x. My goodness. Right, so we have the third one.
But how is 4/3? So
Well, this one here is
it's 4.
1 1/4. Oh, sorry. It's 3/4.
Yeah.
So 3/4 of the wave equals, yeah,
X, so X equals...
4/3.
Yeah.
This is not easy. I know it's not easy. So anyways, let me just write it down again. So for the third harmonic, the frequency is 1100, and the wavelength is 4/5L. And then for the fifth harmonic, what's the frequency? 1800, and the wavelength 4/9L. Yeah, for the fifth one there. Yeah. Now, if you were to look at these, can I go to the side here? This is the wavelength here, isn't it? And this is the wavelength here. So if you were doing this, what you would get is, okay, the wavelength would equal 4/5L. Now, in this question, I don't want the wavelength, I want the V. So do you remember V equals lambda F? So here, if I want the V,
So 4/5L equals 4/9L.
yeah, that's it, yeah. But I need to get the V here. So this would be V over F equals 4/5L. If I just get the, yeah. So then V would equal 4/5 L times F. Yes? Yeah, we know the frequency, yeah. And if you were to do it for the fifth harmonic, you would get the same thing. V equals 4/5 L F. And this frequency is different, so I'll just write F5 and F4. Now these should be the same, like you were saying. But what will happen in real life is they won't quite be the same, they'll be a little bit different. And the reason they're a little bit different is because of the L. You see, what's happening here, you have to hit the fork against the pipe. So the length is not quite this, but it's usually a tiny bit more because it's not like the sound wave perfectly starts here. You know, it's like if this is the fork, if I hit it here, the length is for the wave is actually from here to maybe a little bit above the cup. You know, so there's a small error in the L here. So that's what my hint was. I'd say the wavelength plus an error. Yeah. So do we have time to do? We'll just about finish this one here. Okay. What I was looking for?
Do you have that?
No. So we'll just about finish it. What am I looking for?
You don't have anything.
Find the error. Find the error. Okay. So you can think about the error being the L, or you can think about the error being in the wavelength, whichever way you prefer to think about it. I prefer to think about the error being in the wavelength because the length of the pipe doesn't really change. But if you want to think about the error being in the L, you can. So which do you prefer to think about it as? The error is in the V, or the error is in the wavelength?
Wavelength.
You want to think about the error being in the wavelength. Okay, so if I just take this over to the side for the moment, what you're saying then is wavelength plus wavelength for number 3 plus the error equals 4/5 L, and then here wavelength for number 5 plus the error equals was it 4/5? Oh, where's it gone? It was 4/, yeah, that should have been a 9, wasn't it? Yeah, sorry. 4/9 L here. Now I know this looks difficult, but if you think about it, we can change these again. Lambda equals, what did I say? V over F. V over F. So you can change these into V over F plus the error equals 4/5L, and here V over F plus the error equals 4/9L. Which things do we know and which things do we not know? Do we know the L? No. Do we know the error? No. Do we know the V? Yes. Do we know the F? Yeah. So if you think about it, what you have here is two equations with two unknowns. What's the first F, did I say? 1100. So you have 340, isn't it? Over 1100 plus the error equals 4/5 L. And then for the second one, it's 340 over 1800 plus the error equals 4/9 L. Can you get the error and the L here? Yeah, because they're two equations and you can just solve them. So here I'll just write them out as error minus 4 over 5L equals 340 over 1100, and here error minus 4 over 9L equals 340 over 1800, and then we can just solve this, which I'll just do it on my calculator to save time. Yeah, you could just subtract these to cancel the errors, but I'll just do it automatically on my calculator. 1,
How?
yeah,
Error minus 4, it's not the same equation.
it is. Oh,
I think it's missing a sign.
oh, thank you. This should be
Minus.
minus and minus. Thank you very much. That would have given me the wrong answer.
Mm-hmm.
Minus 340 over 1100, and then the next one, 1 minus 4 over 9, 340. So here, the error, wait, please, the error is minus 0.0386. So the error in the wavelength is about 4 centimeters, roughly. And then the length of the pipe,
How is this 0?
huh?
The error you said in the first is minus 0.03 high.
4 centimeters. About. Minus 4
How
centimeters.
minus 0 equals 4
Minus 0.0386 meters.
It's the error for the first one.
Oh, the error for both of them is for the same error.
Oh, the same error.
Yes, because the reason.
Again, two answers.
Yeah, no, the second answer is for the L, the length of the pipe. This is like the X and this is like the Y.
Okay, 1 second. You said error equals minus 0.038.
Yeah, I just rounded it to the 4. Okay, forget that.
Huh?
This is the error.
How did you round up 0.0 to 4?
Because this is 0.04 meters,
Oh, 0.04. Okay. I thought that was a minus.
which is then 4 centimeters.
Yeah, it's minus. Yeah.
Yeah.
The answer is minus 4
Okay.
Yeah. Wait, nearly finished. 1 more minute.
We have to talk to get L, and we can know it.
Wait.
Well, I'll tell you what the L is. It's 0.338 meters. Now, the error is 4 centimeters, and the reason is because when you hit it, the sound wave is not quite starting at the start of the cup. It's 4 centimeters off. So you have to minus 4 centimeters to fix it. This is the error. This is a very difficult one. It's the most difficult one you could get in the exam. But I've bad news for you. Both of these two, I've seen them in exam papers. This is why I asked them. All right.
No.
Why is it easy?